To review from last section, we had that the volume of a solid can be found by summing up an infinite number of cross-section areas. And we found that if the cross-section area depends on the x, where it is along the x-axis, or in other words, that cross-section is perpendicular to the x-axis, that the volume is then the integral of a of x dx, so that area is dependent on the x. And then similarly, if it depends on y, we integrate with respect to y. With the disk and the washer method, we have a region that is revolved around the x, the y-axis, or another line. And that creates a cross-section like a circle. And so with the disk, we had a solid region. And so we just had pi r squared as our area. But with the washer, recall we have a hole. And so we have pi r squared of the larger circle minus the pi r squared of the smaller circle. And so with the ones that depend on the x, so when the radius depends on the x, we have in terms of x, we saw that. And we also saw that when it depends on the y, we integrate with respect to y, similar to what we discussed with just general areas. Well, today we're going to look at a special curve. So for instance, if we have this curve here, y equals 2x squared minus x cubed, and we have the region bounded by that curve and the x-axis, so this one right here, and we want to revolve it about the y-axis. With the previous methods, we would need to know what the little radius is and what the larger radius is in terms of y, because our cross-sections are perpendicular to that y-axis. It depends on the y. But as you can see, in both cases, that little r and the big R are represented by 2x squared minus x cubed. So what can we do with this? What is our r and our big R? Well, with this scenario, we actually cannot use the disk and the washer method. It will be extremely difficult. So what we're going to do instead is look at a different type of cross-section, and that's going to be shells. Now when it comes to shells, a good image to have in your head is a paper towel. So with the paper towel, you have multiple cylinders. So consider this region wrapped around, revolved around the y-axis. So a paper towel roll that's kind of cut off. And so what we have are multiple cylinders throughout the whole entire paper towel roll. What we're going to do is we're going to use each one of those cylinders, those shells, and find the area of it. Well, what we're going to do is we're going to take one slice of it, so one of those shells, and we're going to find the volume of that shell. So here, to find the volume of the shell, we're going to expand it out, so slice it and expand it, and we notice that the length of this is the circumference of that shell, the height is still the height of the shell, and then the thickness is that delta x. As a result, we have the volume is going to be the circumference times the height and times the thickness. And as we know, our circumference is 2 pi r, our height we're going to let be h, and our thickness are delta x. And now that we know the volume of one of these shells, we're going to use that to find the total volume of the solid. And so here, we have the volume is this. Our total volume then can be approximated by adding up all of those volumes of the shells that we have. So again, having that imagery of the paper towels, we have multiple shells. And with that, we're going to then sum all of those volumes up. So we have the summation from I equals 1 to n of that 2 pi rh delta x. And again, just like we did with Riemann sums, to get a better approximation, we're going to increase that number of shells to infinity. So our volume is going to be now the limit of that summation of all of these volumes. And as you know, again, us mathematicians are lazy, so we represent that using the integral. So we have the integral from a to b of 2 pi rx h of x dx, where your radius and your height depend on that x. Let's look at an example to get a better idea of what's going on. So here I ask you to find the volume of the solid formed by revolving the region bounded by y equals 2x squared minus x cubed. So that initial example, and the x-axis, and we're going to revolve it about the y-axis. So here, again, with our initial example, we have this region, and we want to revolve this about the y-axis. To understand what the shell looks like when we revolve it about the y-axis, what we're going to do is we're going to choose a point, so say this point right here, and we're going to revolve that point about the y-axis, And we're going to then draw a cylinder from that. So what you should end up getting is something like this. Now, one thing to note is that this cylinder here, its radius depends on the x. It really depends on where you're going to draw that cylinder, what point you choose along the x-axis. And the height also depends on the x. And so because of that, we need to find the radius in terms of x. And so what we're going to do is we're going to take the right point minus the left. And one thing to remember is the radius is always the simplest function that you can have. And so here, the right point is just x, and then the left point, we're going from x minus the left point, which is 0. It's x equals 0. So we're going to get x. Now similar, to find the height, again, it's dependent on the x. We're going to take this value here and subtract, so it's top minus bottom. And so it's the y value here, 2x squared minus x cubed, minus that bottom. So we have 2x squared minus x cubed. So that's our top minus the bottom, and our bottom function is just y equals 0. And now there's only one more thing to determine, and that is the bounds. To determine the bounds on our x, we're going to look at the cylinders and decide what x values are needed for all these cylinders. So as you can see here, we're going from 0 until this intersection point. To find this intersection point, what we're going to do is take that original equation. So we had y equals 2x squared minus x cubed, and we're going to set this equal to 0. So setting this equal to 0, so we have 2x squared minus x cubed equals 0. Solving for x, what we get is either x equals 0 or x equals 2. And we already have the 0, and now our intersection point over here is going to be 2. So our bound then is going to be from 0 to 2. With that, and with our equation up here, we're able to find the volume. So our volume is going to be the integral from that bound, so 0 to 2, of 2 pi rx, that radius, which is x, times, now our height, 2x squared minus x cubed dx. And again, the thing to remember is that this part right here, this 2 pi r, is your circumference. And then this part is your height of that cylinder. And that is how you set up the volume for shells.